Hello everyone, welcome back to this video. So in this video, we're going to look at a few things. Number one, we're going to look at the factors that would affect productive collision. Number two, what is the definition of rate of reaction? And then we are going to learn the calculation for rate of reaction. So first thing, from the last video, you were asked to go and find out factors that would affect productive collision. I hope you have found a few. So in this particular, now I'm going to demonstrate to you one way that would affect productive collision. There will be two scenarios shown. I would like you to observe each of them carefully. Scenario number one. Okay. Now, scenario number two. What do you observe? It's quite obvious that in scenario number two, the colliding particles are actually moving at a much higher rate. Yeah, they are moving very fast if you were to compare to scenario number one. So just imagine if you and your friends are also running around blindly, like running around really quickly, the chances of your bumping into each other is definitely higher as well, right? Therefore, scenario number two would definitely produce a higher rate of productive collision, therefore more products. Okay? Yep. So number one, the speed of movement of the molecules could affect productive collision. But then again, what factor do you think would in turn affect the speed of movement? Try to imagine yourself. Under which condition would you be able to run faster? Number one, when you are starving, super hungry, you have not eaten for a long time, you got no more energy. Or in the second situation where you just had some, high sugary drink, and you are now full of energy. Of course, when you are full of energy, you are able to run faster, right? The same applies to the particles, meaning the speed of movement of these particles would definitely be higher when they are filled with energy. And the energy that I'm talking about here refers to kinetic energy. Therefore, kinetic energy in the particles could definitely affect productive collision. Right, let us now observe this second picture to learn about the second factor that would affect productive collision. I would like you to take a moment to observe these four pictures and think and tell me what are the differences between the pictures. Done? What do you see? Now, you see in all four pictures, they are made up of two similar molecules. All the pictures have this green and white molecule. Yeah, all of them have it. The other one that is also found in all the pictures would be this molecule. The black and the white ones. Yeah, all found. But the differences would be how they are colliding into each other. Or rather, you can say that the orientation of how the particles are colliding into each other are actually different. So, by the way, not all collisions here would lead to a product formation, yeah? Okay, in fact, out of the four, only collision number one would produce a product. So this tells you something, class. That is, the orientation of the colliding particles is also very crucial to ensure that a productive collision will take place. If they are colliding in a different or wrong orientation, then no products would be formed. Okay, so now that you know productive collision would produce products in a reaction, we can then relate it to this term called the rate of reaction. What is the rate of reaction? Now I'm going to use pictures again to demonstrate to you what rate of reaction really is. So just imagine if you have a simple reaction here. Reactant A, represented by this star, would be converted to product B, represented by this square. Imagine if there are two examples now, okay, and assuming that these two are two different reactions happening separately. This is one, and this is another one. Okay, both reaction 1 and reaction 2 start off with the same amount of reactant, which is 8 reactants. Yeah, they both start with 8 reactants. But then after 30 minutes, in reaction number 1, see what happens. Out of the 8 reactants, 6 have been converted to become products already. That's why you see 6 products here, only 2 reactants left. Whereas in reaction number 2, out of 6 reactants, only 4 has been converted into the products. Another 5 has been converted into the products, and 3 remain as the reactants. So what does this tell you, people? Yeah, it tells you that after 30 minutes, 5 reactants have been consumed, or you can also say 5 products have been produced. And this applies to reaction 2 as well. So in short, the rate of reaction can be described as the rate of formation of products, or the rate of consumption of the reactant. Rate meaning how fast. Yeah, so how fast the products can be formed, or how fast the reactants can be used up. So look at these two reactions and think and tell me, which one do you think has a higher rate of reaction? The answer is, yep, reaction number 1. Higher rate of reaction because within the same period of time, reaction number 1 actually converted more reactants into products. Therefore, they are said to have a higher rate of reaction. So this is what I mentioned just now. And by the way, there are actually 2 types of rate of reactions that we could actually calculate. One type is called the average rate of reaction. The other one is called the instantaneous rate of reaction. Now the difference between these two is average rate of reaction refers to the change in the quantity of the product over a longer period of time, whereas instantaneous refers to that exact or the particular instant of time. Okay, let me show you the differences in the calculations. This graph shows you the changes of a concentration of a substance over time. Now, can you deduce on your y-axis, what is this? Is this a reactant or is this a product? I hope you got it right, okay? Actually, this is the reactant's concentration, because you can see over time the concentration actually drops. It means that the reactants are being used up, okay? So can you ignore this for a while, this two for a while? Let's just calculate the average rate of reaction here for now. So to calculate the average rate of reaction over 900 seconds, we have to take into account the initial reactant and the final amount of reactants left. Therefore, it will be equals to 0.1 minus 0.0107, okay, here, divided by the total amount of time, which is 900 seconds. So if I were to work it out, I get this 9.22 times 10 to the power of minus 5 molar per second as my average rate of reaction. Okay, remember, average rate of reaction over 900 seconds would include the changes of concentration throughout the 900 seconds. Whereas if you were to calculate instantaneous rate of reaction, given a graph, you will have to draw a tangent, this triangle. If let's say question was asking for you for the instantaneous rate of reaction at 600 seconds. So what you do here is 600 seconds. At this point, you actually draw a straight line. So after you draw the straight line, what you do is you draw a triangle from the straight line, and you actually calculate the change of the concentration using this triangle, that is 0.0402 here minus 0.0109 here, okay, and you divide by the horizontal change, which is 800 minus 400. Yeah, basically using this triangle as a guideline to calculate the instantaneous rate at 600 seconds. So when you do this, you get an answer of 7.33 times 10 to the power minus 5. Okay, we are done with this video because you have already learned how to calculate the rate of reaction, and you have also learned the definition of the rate of reaction. So as your homework of the day, I would like you to then go and find out more about the factors that could affect the rate of reaction. So, what are the things that could actually increase the rate of reaction, or what are some of the things that could actually decrease the rate of reaction? And the discussion shall be done in class. Thank you very much.